Welcome to today's paper reading. Today's paper is titled, Let Me Speak Freely? A Study on the Impact of Format Restrictions on Performance of Large Language Models. This paper, published on the AR14 preprint, explores the impact of format restrictions on large language models' performance by Ji-Rui Tam and colleagues from Adhere AI Research and National Taiwan University. This study examines the effects of structured generation on large language models, LLMs. Structured generation involves producing content in standardized formats such as JSON and XML, which is commonly used in real-world applications to extract key information. The research investigates whether these constraints impact LLMs' abilities, including reasoning and domain knowledge comprehension. Specifically, the study evaluates LLMs' performance when restricted to structured formats versus free-form responses across various tasks. The findings reveal a significant decline in LLMs' reasoning abilities under format restrictions. Additionally, stricter format constraints generally result in greater performance degradation in reasoning tasks. The study's code and results are available online. Large language models, LLMs, have demonstrated impressive few-shot learning and instruction-following capabilities, enabling them to tackle various downstream tasks. However, a significant challenge in deploying LLMs in industrial settings is their inconsistent output formats, which complicate parsing and reduce reliability. To address this, structured generation methods have been proposed, such as enforcing output in standardized formats like JSON or XML. These methods include format-restricting instructions and industrial solutions like JSON mode and instructor, which simplify parsing and integration into real-world applications. Recent research has focused on evaluating LLM's ability to follow formats, but a critical question remains: do format-restricting instructions affect the quality of generated content? This study aims to systematically investigate this relationship, observing performance degradation under format constraints and proposing strategies to mitigate these issues. Figure 1 illustrates the performance of GPT 3.5 Turbo on GSM-8K math questions. When prompted in standard natural language, GPT 3.5 Turbo answers correctly. However, when format restrictions are applied, the model fails to provide accurate responses. This demonstrates a significant performance degradation due to the imposition of structured output formats. In this study, 3 methodologies are employed to examine the impact of different levels of format restrictions on downstream performance. The first method is constrained decoding, which limits the output of large language models by enforcing a predefined token space. This is particularly implemented in JSON mode, a feature available in OpenAI and Gemini APIs that ensures the output is valid JSON. The second method is format-restricting instructions, which direct the LLM to generate responses in standardized formats like JSON, XML, and YAML, ensuring structured output without enforcing a predefined token space. The third method is NLTO format, a two-step process where the LLM first answers in natural language and then converts the response into the target format schema. This method is the most relaxed, decoupling content generation from format adherence. Figure 2 illustrates the performance of different format restrictions on reasoning tasks like GSM-8K, last letter, and shuffled objects. The results show that JSON mode, which enforces a predefined token space, performs the worst in most cases. Format-restricting instructions, FRI, and NLTO format, which are more relaxed, yield better results. Natural language NL prompts, being the most relaxed, are typically the most effective in these reasoning tasks. In this section, we discuss the datasets and tasks used for evaluating the models. For reasoning tasks, we use GSM-8K, which consists of mathematical problems in natural language, last letter concatenation, which tests symbolic reasoning, and shuffled objects, which evaluate state inference. For classification tasks, we employ DDX Plus for medical diagnosis, Multifin for financial classification, and sports understanding to test sentence plausibility. The evaluation methods include task-specific metrics, with exact match used for reasoning tasks like last letter and GSM-8K, and accuracy used for classification tasks such as DDX Plus and Multifin. Figure 3 illustrates the performance of various models on classification tasks using datasets like DDX+, Sports, Task 280, and Multifin under different levels of format restriction. The figure highlights how format constraints affect the accuracy of model outputs, particularly in classification tasks that require structured responses. It shows that while some models benefit from JSON mode restrictions, others maintain competitive performance across various formats, indicating a nuanced impact of format restrictions on LLM performance in classification tasks. The study examines the impact of format restrictions on large language model (LLM) performance through three prompting approaches: JSON mode, FRI, and NL to format conversion. These approaches are evaluated on datasets with exact match scores, including GSM-8K and last letter concatenation. A surprising result is that JSON mode performs significantly worse than FRI on the last letter task, due to the order of keys and responses. Comparing NL to format with unrestricted natural language responses, nearly identical performance is observed across most models, though NL to format introduces occasional generation errors. The study also highlights that JSON mode can significantly boost performance in classification tasks, as seen in the DDX Plus dataset with Gemini 1.5 Flash. The study investigates the effects of looser format restrictions on LLM performance. Removing schema restrictions led to significant improvements in average scores and lower standard deviations across various models, indicating that overly restrictive schemas may hinder performance, especially in reasoning-intensive tasks. When comparing different formats like JSON, XML, and YAML, no single format consistently outperformed others across all models. JSON performed better in classification tasks due to its restricted answer space but failed in reasoning tasks. Parsing errors were found not to be the primary cause of performance differences, but corrective prompting can effectively mitigate them, enhancing the reliability of structured outputs. Table 1 highlights the effects of removing schema restrictions on the GSM-8K dataset. The table shows significant improvements in average scores and lower standard deviations across different prompt perturbations for models like Claude 3 Haiku, GPT 3.5 Turbo, and Llama 3.8b Instruct. These results indicate that overly restrictive schemas may hinder LLM performance, especially in reasoning-intensive tasks. The findings suggest a balance is needed between structured outputs and preserving LLM's reasoning abilities. Figure 4 presents a comparison of different formats and classification tasks across datasets like DDX+, Sports, Task 280, and Multifin. The figure shows the average accuracy for each format over 9 different prompts, along with the standard deviation error. Notably, the performance varies significantly across JSON, XML, and YAML formats, indicating the impact of format choice on model accuracy in classification tasks. Figure 5 illustrates the effectiveness of using a second prompt to correct syntax errors in responses, thereby reducing parsing errors. This method was applied to models with high parsing error rates, such as Claude 3 Haiku and Llama 3.8b. The results show significant improvements in accuracy for JSON and YAML formats, demonstrating a practical approach to enhancing the reliability of structured outputs in large language models. Table 2 presents the parsing error percentages across various models and formats. Key observations include the variability in parsing errors among different models and formats, with Llama 3.8b exhibiting notably high errors in the YAML format, and Claude 3 Haiku showing significant errors in JSON. These findings underscore the importance of format-specific error rates in evaluating model performance. Figure 6 compares the performance of JSON, YAML, XML, and natural language (NL) responses in reasoning-related tasks. The data reveals that NL generally performs better than the other formats, with the notable exception of GPT 3.5 Turbo, which shows competitive performance with NL. This comparison highlights the effectiveness of NL in reasoning tasks, while also indicating specific instances where other formats might be more suitable. Thank you for watching.